ஆன்டிவைரஸ் போட்டதுனால பிரச்சனை.
Sir, shall we start? Sir, good morning, sir. Shall we start, sir?
Yes, Bhaskar.
Yes, sir.
Dean madam available?
Yes, sir.
Okay, madam.
Sunshine is a welcome thing. It brings a lot of brightness. Good morning to all dignitaries, delegates, and participants with great joy and immense exultation. I feel privileged to extend my warm welcome to all connected here for the Department of Biotechnology sponsored one-day online seminar on biotechnological application using a fiber optic sensor, organizing by Department of Electronics and Communication Engineering of Cognado College of Engineering and Technology. You invoke a new future when you envision your past in the light of your present. In this way, now I like to call upon Dr. M. Dharmalingam, Professor and Head of EC Department of Cognado College of Engineering and Technology, to welcome this gathering. Please, sir.
Good morning to all. So this one-day seminar on biotechnological applications using fiber-optic sensors, which is sponsored by DPT, Department of Biotechnology, sponsored by DPT. So for this, I am very happy to welcome you all. Then I am very happy to welcome our chairman, sir. Now, because of some another functions is going on, so he is not available in this program. And I am welcome our principal, Dr. R. Azogan, sir. And I'm very happy to welcome one of the key person for getting this type of funds and organizing any hackathons. Yes, I'm very happy to welcome our Dean Madam, Dr. J. Yogapriya Madam. Then today's chief guest, and also the first session going to handled by Dr. K. Srijit, IITDM, Indian Institute of Information Technology, Design and Manufacturing, Chennai. Really, I am happy to welcome you, sir. I am very happy to welcome the participants. So we received more than 500 and around 600 responses we received. So due to some restriction, we limited to 300 and 400, but till now it is around 100 participants only available in the online. So anyway, I am very happy to welcome all the participants from various institutions and various industries. I am very happy to welcome our department faculty members and students, PG students, and especially the PG students for organizing this one-day seminar, online seminar on biotechnological applications using fiber optic sensors. And once again, I welcome you all. Thank you.
Thank you, sir. Talent win games, but teamwork and intelligence win championship. In this way, now I request Dr. J. Yogapriya ma'am, Dean Research and Development of Kogunadu College of Engineering and Technology, to inaugurate this gathering. Please, ma'am.
So, good morning, one and all present here. First of all, I would like to welcome all the participants from various colleges to learn about the biotechnical applications using fiber optic sensors, which is sponsored by DBT, Department of Biotechnology. First of all, I would like to thank DBT, who has always supporting us to organize various events with relevant to recent technologies. Particularly in this seminar, you will have two sessions. First session is by Dr. K. Srijit sir, and second session by Dr. N. Ayana sir. First of all, I would like to thank these two professors who has accepted an invitation to take the session for this wonderful day. And also I request all the participants to learn about this biotechnological applications by using an fiber optic sensors. In general, DBT always supports that is healthcare and biotechnological applications with relevant to any engineering technologies, right? And also, after learning this seminar, I kindly request everyone to take further research in this particular area and should have an problem idea generations. From that, what are the problems are there currently, and what are the solutions will be available to solve those problems. And you have to arrange with some students. You have to gather it as a students and make it as an make them to available to participate in various hackathons. Say for example, recently the Ministry of Education and AICT is organizing a Smart India hackathon, wherein there are a lot of problem statements has been given in the portal. So relevant to biomedical, biotechnology, as well as electronic stream, computer stream, all the engineering area they have covered it with various ministries. So really it is a wonderful, it will be a wonderful session. From this session, you have to learn about the some fiber optic sensors and how it has been, it will be used for biotechnological applications. I request everyone to take part in that. It should be an interactive session. Kindly interact with the resource person. Definitely they will guide you. And also I request all the faculty members to take part the research in this fiber optic sensor and publish our papers and findings in international conferences as well as an SCA indexed journals. So then only our profile also will be will be shown to everyone. And also you are performing some wonderful research. Everyone in every colleges, whatever auditing we are going for NBA or NAC and autonomous, if we are going to get, means definitely they are asking whether the faculties are updated with the latest technology like that, right? So based on how we are going to evaluate, means based on our publications, patent and research projects, whatever you are having it, how we are guiding the students, everything they will ask. So it's general guidelines. Request everyone to take part in this and get clearance, and it should be an interactive session. And also I would like to thank Professor HOD Dharmalingam sir and Benistina and Amuda madam and our ME student Bhaskar. Everyone has taken part in this to organize this online seminar. Thank you one and all.
Thank you, ma'am. Darkness cannot drive out the darkness, only light can make it. In this way, now I'd like to welcome our today's resource person, Dr. K. Srijit, Assistant Professor, Department of Electronics and Communication Engineering, Indian Institute of Information Technology, Design and Manufacturing, Chennai. Welcome you, sir.
Thank you for the kind welcome.
Yes, sir. Now I like to call upon Ms. K. Dharani, final year ECE, to give her the short intro about resource person.
Good morning, everyone. A great thing can only be done by a great person. I feel glad to introduce such a wonderful guide and today's resource person, Dr. K. Srijit, Assistant Professor, Department of ECE, Indian Institute of Information Technology, Design and Manufacturing, Kanchipuram. He graduated with a PhD in photonics from IIT Madras for working on identification, classification, and localization of partial discharges in power transformers using fiber brack gratings. He obtained his BTech degree in ECE from Rajagiri School of Engineering and Technology, Kerala, and MTech degree in Communication Systems from NIT Trichy. His research interests include for fiber optic sensors. He is a member of Optica, SPY, IEEE, and ISTE, and a mentor of Optica students and faculty. He is an inspiring person who have great knowledge. So without wasting, let's gain knowledge from our Dr. K. Srijit, and I proudly hand over the session to him.
Thank you very much for the kind introduction. At the outset, let me thank the organizers for giving me this opportunity to present in this DBT-sponsored seminar on biotechnological applications of fiber optic sensors. I thank all the faculty and HOD and Dean for inviting me over to this session and giving me this opportunity. All right. Shall I get on with the talk? Is it okay if I can share my screen now?
Yes, sir. You can start your sharing, sir.
Is my screen visible?
Yes, sir. It's visible.
Okay. All right. So today we are talking about biomedical applications of fiber optic sensors. And before I start off, I would like to know what is the audience group consisting of? Uh, is it mainly students or is it like faculty? So, Bhaskar, can you please answer this question?
Yes, sir.
No, what is the audience group consisting of? Is it mainly students or faculty?
Uh, Faculty, sir.
Okay, nice. All right, thank you for that information. So, as the person introduced, I am Srijit. I'm an assistant professor in the Department of ECE at IIITDM Kanchipuram. Before I start off, let me give you an idea about our institute. So we are one of the centrally funded technical institutes, one of the 5 centrally funded IIITs. So we are IIIT with a special mandate on design and manufacturing. We are located, although our name says Kanchipuram, we are located very much close to Chennai. The airport is just half an hour drive from here, and we are just 11 kilometers from the GST road. So we are pretty much in Chennai, although our name says Kanchipuram. And this is a bird's eye view of our campus. Of course, this is a pretty much old pic. I should probably replace it with a newer one. You could see that there are a couple of more buildings up now. So we have 5 departments and an interdisciplinary school. So we have computer science, electronics communication, mechanical, recently inducted biomedical biotechnology department, sciences and humanities, and we have an interdisciplinary school which is called as the School of Interdisciplinary Science and Innovation. And we offer BTech, dual degree, MTech, and MDes programs in addition to PhD. I should also mention that we are one of the recently inducted QIP centers, QIP AACT QIP center, a minor center, and we are starting to offer PhD program under QIP from the upcoming academic year onwards. So, and as part of the QIP center, there are a couple of short-term courses running in the department, running in the institute for the past one month. Those who are interested in pursuing a PhD under QIP, you might want to check out our website, look at the kind of department programs running in the department and specializations and so on. All right. So this is going to be the outline of today's talk. We'll start with the motivation for biomedical sensing, and the next question that we'll answer is why fiber optic sensors, why optical fiber sensors in particular. Why do you, we have a lot of other sensing technologies available. What are the advantages that optical fiber sensors offer? Okay, and then we'll talk about one technology for sensing, which is based on an element which is known as a fiber Bragg grating. Okay, so we'll talk about this device, and we'll talk about the principle, working, and applications of this device, and then we shall take up a couple of case studies where the sensor has been employed for the biomedical application. So we'll talk about biomechanical sensing, some applications in biochemical sensing, and in general some biomedical sensing related applications. And then I'll conclude and also highlight what are the research opportunities in this field. Okay, so it's been 2 years into the pandemic, and we know how important healthcare technologies have been evolving in the past 1 or 2 years. So overall, there's a across the globe there is a high demand for healthcare related technologies, and some of the desirable features which people are looking for are non-invasiveness. Any kind of diagnostic tool that you want to look at, you're not interested in any invasive kind of technology. Rather, you would want a non-invasive. So when I say non-invasive, it essentially means that any kind of diagnostics which is not not entering into your body, in the sense that there is no cut that is being made, or things like that. So non-invasive technologies are gaining a lot of importance, and there are a lot of technologies available as of today. And you talk about the other domain of surgical procedures. You always would want minimally invasive surgical procedures. So you very well know nowadays that how laparoscopic surgeries have taken over the traditional open surgery, right, for a variety of procedures. So the demand for minimally invasive procedures is on the rise. So it's much easier for the patient as well, for the recovery and subsequent getting back to the old getting back to normal life. Okay, so but all this, we should acknowledge the fact that all this is possible because of the advancements in technology and engineering. A recent buzzword nowadays, everybody would be talking about Internet of Things, and also people start talking about the cyber physical systems, where now you are thinking about a lot of sensors being involved in taking measurements in the body, or for example in a hospital room. When there's a patient, there's a lot of sensors which are monitoring the physiological parameters of the patient, and all this start now sending data to the cloud. And you could start making predictions, you could start taking appropriate actions based on that data that is available in the cloud. So all this data science, artificial intelligence, machine learning, all that is making sense because you have a lot of data available. And where do these data come from? They all come from sensors. And so it is the sensors that actually generate the raw material for data processing, for data scientists and people trained in machine learning and so on. So IoT is slowly starting to make its presence in the health domain as well. And as years come by, we will start seeing more and more applications of IoT enabled e-health. Okay, so this is a prediction done on the optical sensors market, and you can see that it's predicted that in the next couple of years, you can see that the market share is almost doubled, more than doubled within a just short span of 8 years. So it's been a cumulative average growth rate of 11% is predicted in the uh, optical sensors. And if you look at the global biosensors market, what are the different products that are available? Almost 50% or more than 50% is being dominated by technologies related to clinical diagnostics. Things like, starting from very simple things like analyzing the hemoglobin count in the blood to very complicated things like checking for certain specific antibodies or for checking certain diseases, whether you want analyzing the body samples and predict and checking if there's this virus, for example our COVID test. So all sort of clinical diagnostics is the major share which is being held. It's a clinical diagnostics which holds the major share in the global biosensors market. Okay, so I'm just trying to highlight the fact that you have a lot of opportunities with sensors in this medical field. Now, there's another publication, a figure which is picked from a publication, past I think 2 to 3 years back. So here they are trying to show the relative share of different technologies for these biomedical applications, and you can see that there's a steady growth in the optical fiber related technology. So this is like the number of publications which have been which are coming up in this area, and it clearly shows that there's a lot of interest among the different research communities across the world in applying optical fiber related technologies in biomedical engineering. Okay. Now, as I told you, it's not just diagnostics that fiber optic sensors make their presence, rather in a variety of other applications related, allied applications as well. So you start from diagnosis, you talk about things like endoscopy, optical coherence tomography for, for imaging, and then, very simple things like detecting level of glucose in blood. These are some of the diagnosis related applications. And if you talk about monitoring, we have, the pulse oximeter. It was quite a hit in the last, especially during the first wave, when all the COVID patients were monitored using this pulse oximeter. And do you realize that this pulse oximeter is an optical sensor? It's basically, the principle is based on optical sensing. And then there are, other applications like blood pressure monitoring, respiratory rate monitoring, a lot of physiological parameters monitoring, and so on. If you look at the treatment, we have applications of optical sensing in robotic surgeries, in magnetic, MRI procedures, MRI guidance. We use optical sensors, and this is there's also one. This is more like RF hyperthermia, where you want to selectively, kill out cancer cells or something with temperature. And when you talk about care, patient care, elderly care, there are applications in posture monitoring to check the bed occupancy status, physiotherapy and rehabilitation purpose. And also, nowadays people start talking a lot about wearable sensors. So that's also something which fiber optic sensors are also making their presence. Okay, so this is it's an overview of the different allied areas in healthcare and what are the possible applications of optical sensors in all of these. Now, when you start talking about diagnosis, there are different biomedical parameters which people are interested in, starting from body temperature, heart rate, shape sensing, respiration, and glucose, all these chemicals, biochemicals, antigens, antibodies. So you name it, we have some solution with fiber optic sensing. And I should also mention there are a lot of imaging applications as well. For example, endoscopy is basically an imaging procedure. Optical coherence tomography is also imaging kind of applications where you use light. Now, there are already a couple of commercial products available in the market. For example, for temperature sensing, pressure sensing, coronary imaging, pulse oximeter, of course, that's quite familiar to all of you. Force, blood flow meter. So there are a lot of commercial products already available in the market related to biomedical sensing. I'm talking about optical technologies here. Okay, so it's quite boring if I keep talking. So let's start doing a couple of interesting activities. So let me just go back to here. Yeah. So I would want all of you I'll probably post this link in the chat window. Yeah. Or if you're, you can just click on the link and you can answer this question. What do you think are the advantages that fiber optic sensors offer? Now, you needn't be an expert in this area, based on what your understanding. Just list out what do you think would be the advantages that fiber optic sensors can offer. You can, to answer this, you can basically click on that link in the chat window. It will, pop up a window and you can answer the questions. So I'll wait for a couple of minutes, maybe two minutes. I see that nobody has responded so far.
Okay, sir.
Yeah, I can see one response. So how many participants do we have? We're close to 89. Please don't hesitate to participate. Your answer could be right or wrong. It's just, just a game. You can think of it as a game. Just, put in your comments. All right, I'm seeing 10 responses now. Probably I'll wait for one more minute. Okay, I don't think the other people are responding. So, we're trying to see who are the actual people listening to what we are saying. Okay, so I have got these responses: high sensitivity, um, flexibility, small size, non-invasive procedure, lightweight, more sensitivity. Okay, high immunity, bandwidth, yes. Um, Less loss of signal strength, yes. Medical imaging procedures, immunity to EM. Well, that's a very important point. Nice that somebody has pointed it out. Smart world. Okay, so I think the most or the largest number of people have mentioned sensitivity to be one of the key reasons why one of the key advantages of fiber optic sensor. Okay, so thank you for all the 13 participants who took part in this. Let's get on with the session. So, people who are not able to participate in this, I have one more activity coming up, and it's going to be a quiz. So, I want all of you to pay attention to what I'm talking about, so that you can let's see who's going to be the winner. Okay. All right. So, yeah, the question that I asked you is why optical sensors, specifically fiber optic sensors. As somebody has pointed out, fiber optic sensor is basically, when you talk about optical fibers, we generally use glass for making these fibers. Okay, so glass is basically a dielectric material, which means the biggest advantage that you get with an optical fiber is the immunity to electromagnetic interference, or uh, you know um, when you have external electromagnetic disturbances, that's not going to affect the signal in your optical fiber. Okay, that's a very, very big advantage which optical fiber sensors offer. Okay. Yeah, the other things like it's basically non-conductive because it's dielectric. It's biocompatible, of course, it's just glass. And in fact, we also do some kind of coatings on glass to make it, when you are making it interact with the body tissues, we embed these fiber optic sensors in certain materials which are biocompatible. Okay, so it's you can easily integrate fiber optic sensors with all those kind of biocompatible materials. Okay, yeah, and this point somebody had pointed out, it's small size, so it's quite flexible. The size I'm talking about is the diameter of an optical fiber is something like 125 micrometers, something between 100 and 200 microns. Yeah, it's non-invasive, minimally invasive kind of, and it's also ideal for sterilizable and disposable applications, because thanks to the communication industry, people always associate fiber optics to fiber optic communication, because communication is the most uh, the most deployed uh, application of fiber optics. But then there is also an equally major growing field of sensors based on fiber optics. Okay, so because the fiber optic communication is a fairly mature technology, you have all the components available for building a fiber optic sensor. Okay, so any sensor, if you think about, would naturally need a source of light and something to detect light. So these sources and detectors are quite easily available in the market, because already they have been made for communication. Okay, we'll talk more about that in the upcoming slides. Now, if you talk about the level of maturity of fiber optic sensors, is also picked up from a paper. There are certain areas where fiber optic sensors have already shown a fairly good level of maturity. For example, sensors to monitor intracranial pressure and intra-aortic balloon. and reasonable progress has been made in respiratory sensing, tactile sensors, thermal ablation, and robotic eye surgery kind of applications. But there are certain areas where still work is going on, making prostatic implants, personalized drug delivery, and things like that. So this basically to show you that there are certain areas where fiber optic sensors have shown a pretty good level of maturity. Now, this is one of the first applications of optical fibers in clinical diagnosis, which is basically endoscopy. I'm sure all of you must have, I mean, everybody would know about endoscope because it's basically a it's basically an optical fiber where you pass light onto the optical fiber and you try to illuminate the internal organs, and you can view it on there's a camera which is also attached at the end of the fiber tip, and that camera will transmit the signal to the monitor there, and you're able to visualize the doctor is able to visualize the internal organs. So this was one of the very first applications of optical fibers in medical diagnosis. Now I talk about optical fiber, and I'm really not sure what is the understanding that the crowd has about optical fiber. So let me get into some of the basics of optical fiber so that you appreciate what I'm trying to talk about. Okay. So an optical fiber, probably in your schools you must have learned this. It has a core and a cladding, an inner core and an outer cladding. Core has a higher refractive index than the cladding, right? These things you might be familiar with. So what are we talking about here? You have an inner core which is typically of the order of less than 10 micron diameter, and that is where your light signals are getting confined. Okay, so the core is the part of the fiber which carries your light, and mind you, this is thinner than your hair. Okay, it's as small as that. And then you have an outer cladding which is having a slightly lower refractive index, which helps to confine the light within the core. And this cladding and core, they are not independent entities, meaning you cannot just pull the core out of the cladding. It's not like that. It's just that their refractive indices are different. Both are made of the same material. Okay, there's doping done on either at the core or the cladding to make its refractive index different. And then, there are coatings. So I've just shown one coating here, which is basically to protect the glass. It's primarily an acrylic coating. So that coated fiber, overall it will come around 250 microns in diameter. And then, you could now start bundling many fibers together, and then,
Sir, excuse me, sir. You are not audible. Srijit, sir, we can't able to hear why. Dear participants, due to some technical issue, this person has left. So kindly hold on. He will join as soon as possible.
Sorry, I faced a network issue. I'll
Yes,
just
sir.
continue.
Now we can able to hear you.
Okay, okay. So could you please let me know which was the last slide that you heard? Did you hear this one?
Yes, sir. So 13
Yes.
said like when you're speaking about endoscopy.
Oh, until here is what you heard, is it?
Yeah, yes, sir.
Okay, thank you. Okay, I'll start from here. So I was, talking about an optical fiber in general. So please, or you can just call me in case there's a network issue. Um, just that my institute internet has some fluctuations, so that's why. All right.
Yeah, sure, sir.
Yeah, thank you. So I'm talking about the optical fiber. So I'm sure many of you might not be very familiar with this optical fiber, but you must have heard of optical fibers. So let's try to understand what are the different components in and how do you basically construct an optical fiber. So you can see that there's an inner core and an outer cladding, and it is the core which helps to carry the light signals, or where it's in the core where the light signals are confined. So the typical diameter that we are talking about is something less than 10 microns, which is actually thinner than your human hair. Okay, and then surrounding the core you have a cladding which helps to keep the light within the core. Okay, and then you cannot this core and cladding are not separate entities. You cannot just pull the core out of the cladding. It's both are made of the same material. It's just that the refractive index is different. Okay, so core has a slightly larger refractive index than the cladding. And surrounding the core and the clad, there is a coating which helps in protecting the glass, and the coating is typically made of a plastic material called acrylate. Okay? And then you start this is a single fiber. Now you can actually group, or you can start bundling many of these fibers into a fiber optic cable. Okay? Now, how does this optical fiber work? As I told you, you have a core and a cladding, and any ray of light which gets incident at the core cladding interface at an angle greater than the critical angle, it will get reflected. This process is called total internal reflection, and then subsequently it gets guided within the fiber. Okay. Now you talk about this ray of light, the red one, which is making an angle which is less than the critical angle, it gets lost. It just gets refracted and gets lost. Okay, so we can define a cone outside the fiber, where this is the cone in which the fiber accepts the light. Okay. Talking about the loss, we are looking at a standard fiber. The loss is something like 0.2 dB over 1 kilometer, and you could make these fibers with either glass or even with plastic. So there are a lot of plastic fibers available, PMMA fibers and all available. And you could make this fiber work as a single mode or multi-mode, which means that you could have just one mode propagating within the fiber, or you could support multiple modes. Okay, I'm not going into very specific details of those. Now, looking at the electromagnetic spectrum, where does our optical window lie? We are talking about this area, which comprises of the UV, visible, and infrared. Okay. Now, this is an electromagnetic spectrum, so you know that light is an electromagnetic wave. It has an electric field and associated magnetic field, and you must be aware of the fact that electric field is perpendicular to the magnetic field, and both of them are perpendicular to the direction of wave propagation. Okay? So if you write down a mathematical expression for an electromagnetic wave, it's going to be something like this, where you can notice that there is an amplitude, or there's an intensity, or there's an amplitude E naught. There is a frequency term which is omega. There is a phase term which is beta z. And you can also notice that the field is polarized along the x direction. Okay, so don't get frightened, because this is the only equation I'm going to show you in this entire talk. Okay, but the point is that this gives us some sort of hint as in how can you start employing these, or how can you start using light for sensing. Okay. So it means that if you want to employ, if you want to build a sensor using light, your physical parameter, or what is the parameter that you want to sense, it has to create changes in any of these four parameters. It could be either change in your intensity or amplitude, it could be change in your frequency, it could be change in the phase, or it could be change in the polarization. Okay. So based on that, we have, in fact, four classes of fiber optic sensors. I'll show that in the next slide. So this is going to be a basic configuration of a fiber optic sensor. Obviously, you will need an optical fiber. You need an optical source to generate light. You need an optical detector, which is called as a photodetector for sensing the light. Okay, so this is a very simple block diagram of a sensor. And once you have this photodetector detecting the light, it will convert into an electrical signal, and then you use some sort of electronic processing. Okay. So as I told you, the perturbation or the sensing parameter is going to create changes in any of these four parameters of light which is propagating through the fiber. Okay. So it is the modulation in amplitude, phase, frequency, or polarization due to changes in, it could be strain, it could be anything. So when I say perturbation, it could be anything. It could be strain, temperature, pressure, any chemical species, anything. Okay. Now, your challenge is going to be demodulating this. Okay, so let us say there has been some change in intensity. Let us say there's some change in phase. How do you understand that? How do you, demodulate that phase change and get relevant information? So that is the key behind or key challenge in all of these sensor systems. Okay. There are also other configurations where you could start using a single optical fiber for multi-parameter sensing, or multiple sensing at multiple locations. Okay. There are also configurations wherein you use reflected light for sensing. Okay. So in that case, both your source and detector is going to be on one side, and your fiber is going to just be laid, or it's just it's a reflection property that we have. So what happens is, the source generates lights, it throws light into the fiber. As the light propagates, depending on the perturbation, there are some reflections that are generated. So reflection is going to come back towards the source, and it is taken to the detector for sensing. Okay. So as I told you, the entire field of fiber optic sensors can be broadly classified into four different categories. You have amplitude modulated sensors, phase modulated sensors, wavelength modulated sensor, all polarization modulated. Okay. Since this talk, I'm not going to cover all these kind of sensors. We'll pick a specific example. We'll pick this, wavelength modulated sensor. So I think now you should be able to recognize what is meant by wavelength modulated sensor. It essentially means that your sensing parameter is going to create a change in the wavelength of light which is propagating through the fiber. Okay, so that's a wavelength modulated sensor. So let me introduce you to this one type of wavelength modulated sensor, which is called a fiber Bragg grating. Okay. Now, this grating, the word grating is probably familiar to you. It represents a periodic change in something, and this is gratings are very well observed in nature as well. So you can see this image here, this beautiful colors that you see in this peacock feather is because of the fact that if you zoom into the structure, you will see some periodic structures which are reflecting a particular color. So if you zoom in, you'll notice that the structures here they are reflecting blue color. The structures here they are reflecting a green color. Okay, so it is the same principle that we try to make use in an optical fiber Bragg grating as well. So let me talk about how do you make fiber Bragg grating, or what is this fiber Bragg grating all about? Okay, so as I told you earlier, I told that you have a core and a cladding in an optical fiber, and we said that the core refractive index is slightly higher than the cladding refractive index. Okay. Now what we're going to do is we are going to create deliberately, we are going to create periodic changes in the refractive index inside the core of an optical fiber for a short length. Okay, so you can see that there are some alternate white and dark regions here, which actually represent, this dark regions actually represent slightly higher refractive index. So you have now a periodic change in the refractive index along a short length in the fiber. Right? And the kind of change I'm talking about is look at this order of magnitude. It's like 10 power minus 4, which means it's of the order of 0.000 one number there. Okay. So it's very small change in refractive index that we are talking about. And mind you, this refractive index change is only there in the core. It's not in the cladding. Okay, it's only restricted to the core. Now let's see what happens. Suppose you send in colors into the grating. You notice that there is one color which gets reflected back. For example, I send in all the 7 colors, and I see that it's the green light which has been reflected back. Is there a... Sorry? Okay, so you can see that there is one, there's a single color which has been reflected back. So if you look at the other end of the fiber, you find that green color is missing. Well, why is it missing? It is missing because it got reflected back. Okay, so this is the principle of a fiber Bragg grating. If you send in a broad band of wavelengths, it reflects one particular wavelength. All other wavelengths are transmitted through the fiber. Okay. Now, if that is the case, okay, fine. So what? How is this going to help as a sensor? Okay, let me also talk about this reflected wavelength. So reflected wavelength is what we call as the Bragg wavelength, and this Bragg wavelength is found to be dependent or directly proportional to the period of the grating. Okay, so this capital lambda represents the period of the grating, and N effective represents the effective refractive index of the mode that is propagating within the fiber. So it's something related to the refractive index. You can take it up that way. Okay. Now the next question is, okay, how do you use this as a sensor? Let us say you subject this device, this fiber, to temperature or strain. What is the thing that you notice here? Well, when the fiber is subjected to temperature or strain, there is some interesting thing that you observe, that the color of the light which gets reflected back has changed. Look at this. Earlier, the grating was reflecting green light. Now, it is reflecting yellow. And if you look at the output part of the fiber, green has reappeared, but yellow is missing. Okay. So the beautiful principle of this FBG as we call it, fiber Bragg grating is usually called as an FBG. So the beautiful principle of this FBG sensor is that any kind of temperature or strain variation is going to create a change in the wavelength of light which is reflected back. Okay, so we call it as the reflected spectrum. So that's the beauty of this grating. So which means for any kind of temperature and strain application, you could use this FBG as a sensor. Okay? In fact, this device, when it was initially discovered, it was not used for sensing. In fact, it was used for some other purpose. It was primarily used as a reflector, as a mirror. In fact, it was initially used as a mirror. It's only later that people found that it has this sensing capability as well. Okay, all right. So now, how is this beneficial? Well, what's the advantage of this sensor? Well, anything that is encoded in wavelength is quite robust. it's not easily affected by noise. For example, just think of it. Let's say you take red light, okay, and you shine it over, if probably the light has, if your light has so much of power that it doesn't diverge, and let's say it can transmit over 1 kilometer distance. Okay, suppose you have a torch like that. Um, you know, the red will remain red color. The color is not going to change, even if it propagates 1 kilometer or 100 kilometers, or even if you send something to outer space. The wavelength is not something which gets corrected, as long as we are talking about a linear medium. Okay. Okay. So the point is that this is quite a robust sensing mechanism, because it cannot be easily affected by noise, as opposed to something like amplitude. Amplitude, you just take the fiber, you bend it, you're going to lose your signal, but not so in wavelength. Okay, so wavelength is getting preserved. Wavelength is not easily affected by noise. Okay, so just to reiterate, the principle of FBG sensor is that any kind of perturbations, temperature or strain, are wavelength encoded, and it is the shift in the wavelength, shift in the Bragg wavelength, which corresponds to the magnitude of the perturbation. Okay, so we can actually calculate what the shift in Bragg wavelength is by looking at the change or the sensitivity of the period as well as the refractive index to temperature or strain. Okay. Now, although I explained it with visible colors, typically these gratings are used in near infrared. It's like greater than 1.3 microns or 1300 nanometers kind of. So this is going to be a typical reflection and transmission spectrum of a grating. So what you see in red is the reflection spectrum. So you can see that there is a small band of wavelengths that are being reflected. So with a peak. So this peak is what we call as the Bragg wavelength. Okay. At the same time, if you look at the other end of the fiber, you will notice that there is a dip in the transmission spectrum, and the dip also corresponds to the Bragg wavelength. So you can either look at the reflection spectrum and notice for the peak, or look at the other end and locate the dip. Okay. Now there are different types of gratings that are available. So we have something like weak gratings versus strong gratings. So it depends on how much is your refractive index change. So depending on that, the reflectivity is going to. So what I mean by reflectivity is this peak. Okay, so the peak is going to increase if it's a strong grating. Okay. Then you have something called as uniform versus apodized gratings. So in uniform gratings, you can notice that this refractive index change, this delta n, the height of these change, or this square waveform, is constant. On the other hand, here the height is not the same. It's maximum at the center, and as it moves to the outer edges, the delta n change is suppressed. Okay. Now this has an advantage of suppressing the side lobes. I think you can see that there are some side lobes here. There are some side lobes. So these side lobes can be suppressed if you use an apodized grating. Okay. Then there is something called as a chirped grating, where the period is not constant across the length. The period keeps changing as a function of distance. Okay. So they have a very broad reflection spectrum, and these are actually used in communication applications for dispersion compensation. Okay. Then there's also another type of grating which is called a tilted grating, where the grating that we talk about, the reflection is coupled to the core itself, but a tilted grating which is at an angle actually couples the light not to the core, but a part of it is coupled to the core, and there's also another part which is getting coupled to the cladding. And whatever is coupled in the cladding, it cannot propagate. It will just get lost after some time. Okay. So these are some of the different types of FBGs that are available. Now the question is, okay, how do you make these gratings? How do you fabricate these gratings? Okay. So there are different ways of doing it. There is this interferometric technique, there's a face mask technique, and there's also this point by point writing technique. Okay. I'm not sure if I should be explaining this about the, I'm not really sure about the crowd, whether they'll be able to appreciate this, but probably I'll just talk about the face mask technique. So here what happens is you have a diffractive element which is called as a face mask, and you use UV light to illuminate the face mask. So this UV light, it's typically at 248 nanometers. And what this face mask does is it creates diffraction. Okay. So maximum diffraction in the plus and the -1 orders. So what happens is these plus and -1 orders, they interfere within the near field, uh, creating an interference pattern. So you can see that there's an interference pattern is probably quite familiar to you. You must have heard of this alternate dark and bright fringes, right? The same thing. You have alternate dark and bright fringes, dark and bright zones here. And now you keep your optical fiber here. You will notice that wherever you have these dark fringes, you have refractive index increasing over there. Okay. Now, what is the mechanism by which refractive index is increasing? That's because there's something called as defect states within the glass, and these defects they absorb this 248 nanometer energy, UV light, and that's how the refractive index changes. Okay. There's also another technique where you don't use a face mask, rather you use a femtosecond laser, and you focus the laser onto the fiber, and you write the grating point by point. So you create one refractive index change, then you move the fiber, create the next one, and so on. So from the name itself, it's very clear. You write it point by point. Okay? That's another way of making gratings. People are now talking about making gratings while the fiber is being fabricated itself. So this is shows typical assembly in a fiber drawing machine, fiber drawing facility. So you can see that there is this preform here, which is basically heated using an oven. So it just melts and it creates this fiber, and then you just pull the fiber down. Okay, so that's the way fibers are made. And you can see that while the fiber is being made, you have used an interferometric setup here for FBG writing. So even when the fiber is being fabricated, you make these gratings, and this is from a company called FBGS. And you can see here that they've made a fiber with 33 gratings in that single fiber. Okay, so that's like 33 different sensing points inside a single fiber itself. Okay. Okay, now the other interesting aspect is how do you start understanding what is the wavelength shift? We said this point, right? We said that any kind of temperature or strain variation is going to create a shift in the wavelength. Now, you're trying to ask the FBG, hey, how much did your wavelength shift? How would you be able to know that? What are the different ways of interrogating the FBG sensors? Okay. So we are talking about that, and primarily they fall into three different categories. You have spectrometer-based interrogation, tunable laser-based interrogation, and a matched FBG-based interrogation. Now, which one to choose will depend on what your application is, whether you're looking at something like a static perturbation or a dynamic perturbation. So when I say dynamic perturbation, I'm referring to something which changes with time. Okay. Then you look at what is the range of your measurement, what sensitivity do you need, and what is the cost you are willing to incur. Okay. So all this will depend on which interrogation technique that you will use. Okay. So one of the simplest technique is the spectrometer-based interrogation, where you use your FBG sensor, use a broadband light source to illuminate the FBG sensor, and then you use an optical spectrum analyzer to capture the spectrum. Okay, and you see a device here. This is called as a circulator, a 3-port circulator, where it allows propagation only in one direction, the clockwise direction. So whatever you input into port 1 gets transmitted to port 2, so that goes to your FBG. And from the FBG, you know that there is a reflection that's coming. So the reflection comes to port 2, it goes to port 3, and it is captured by your optical spectrum analyzer. So this is what you would see in the spectrum analyzer. You will see a peak in the reflection spectrum. Now, what happens when there is a perturbation? Well, when there is a perturbation, the reflection would shift in Bragg wavelength, and that you can read out from a spectrometer, okay? From the spectrum analyzer. So this is fairly a simple technique, except for the fact that spectrum analyzers are a bit costly. Okay, so there is this another technique where you don't use a spectrum analyzer. Rather, you use a simple photodetector, which is very cheap, but then you use a tunable laser source. Okay, it's not in the previous case, you saw that you were using a broadband light source, probably an LED source, but now you're talking about using a tunable source. Okay, so when I say tunable laser, we are talking about a very, very narrow line width, narrow spectrum laser. And what you do is you bias your tunable laser on this reflection slope of the FBG. So you can see that the tunable laser is biased at the slope, and it's only that much light that gets reflected back into the photodetector. Okay, so it is very small amount of light that reflects from the photodetector, from the FBG. Okay, now let's see what happens when the FBG spectrum shifts. What do you observe here? You now notice that the amount of light, the intensity, the intensity or the amplitude of the light which is reflected back is more. Okay, which means what have you done here? You have tried to convert in wavelength change to a corresponding change in intensity, right? So that is the principle behind this tunable laser-based interrogation. You convert wavelength changes to corresponding intensity changes, so that the intensity change can be easily read out using a photodetector. You don't need a spectrum analyzer for that. There is this other technique which is called as a matched FBG interrogation. You know, the tunable laser is also a bit costly on that sense. You know, it's like telling, okay, you replace the spectrum analyzer with a very cheap photodetector, but now you replace this LED with a costly tunable laser source. Okay, so that's also, you know, on the cost perspective, it's not pretty good enough. So then you have another technique where you use both a broadband light source and a photodetector. However, you need two FBGs for this. So you have a sensor FBG and an interrogator FBG. And what happens is, you know, the amount of intensity that is fed into the photodetector will depend on the overlap between these two FBGs. Okay, so you deliberately make the sensor FBG and interrogator FBG slightly different in Bragg wavelength, so that you have an overlap, which you see here. You know, this is the overlap, and that overlap is what is going to be read by the photodetector. Now, what happens when the sensor FBG experiences a perturbation? You can now see that the sensor has shifted, interrogator remains the same, sensor got shifted in Bragg wavelength, and now the overlap between the sensor and interrogator has increased, right? So it is again the same principle that, you know, that wavelength shift is being converted into a corresponding change in intensity, which you can read through this photodetector. Okay. So I've talked about three different interrogation techniques: spectrometer-based technique, tunable laser-based technique, and matched FBG-based technique. Okay. Now it's time for another activity, in fact, a quiz. Okay. So let's see if people were attentive. Okay. All right. So I'm going to copy the link. I would want all of you to please click on this link and join the quiz. Okay, I'll be able to see you here if you have started joining. Yeah, I can see that one person has joined. So I would want all of you to join so that we can start the game in one shot. I'll probably wait for a minute. Just type in your name and you can log in. Okay, I can see that 27 has joined. Is anyone else trying to join? Okay. Okay, so once we start the game, the other people might not be able to participate. So I would request, in case you are interested in participating, please join quickly. I'll wait some more time. Maybe we'll start the game at 11:10. Just one more minute. Okay, so it's 11:10. I'm starting the game. Okay, I think I'll just stop at this time. Okay, so we have the winners here. Thank you for participating. Yeah. Okay, there were two questions which I had asked. The first one was, which interrogation techniques offers the maximum range of measurement? So when you talk about the range as in how much wavelength range we can measure, the maximum range is offered by the first technique, which is a spectrometer-based technique. Okay. The second question that I asked was in terms of cost. I'd already hinted on that. Spectrometer-based technique uses a spectrometer, which is costly. The tunable laser uses a tunable laser, which is pretty costly. So it is the broadband source photodetector combination is which gives the least number of cost, least in terms of the cost. Okay. All right. Thank you guys for participating. Let's get on with the. Okay, so here's the comparison in terms of range, resolution, measurement speed, cost, and multiplexing capability. So as I told you, range, the highest is offered by spectrometer. Why do I say that range is lower for the other two? Because in both the other two cases, you are utilizing the reflection slope of the FPG, and typical reflection width of the FPG is something like 0.2 nanometers, 0.2 to 0.3 nanometers. Okay, so it's pretty much low. In terms of resolution, it is the tunable laser and the match filter which has a better resolution over spectrometer, as well as speed as well. You cannot use spectrometer for dynamic measurements. Dynamic as in something like something which is changing very fast, something like kilohertz or hundreds of kilohertz. You cannot use a spectrometer. Okay? That's when you have to go for these higher other interrogation techniques. Okay, so since I've told you the fundamentals related to the fiber optic, the fiber Bragg breaking, the FBG sensor, let's now start talking about some of the applications, some of the demonstrations in which FBGs have been used for applications related to this field of biotechnology and biomedicine. Okay, so the first one going to talk about is about biomechanical sensing. So this is one of the applications where you are interested in mapping out the plantar strain as in the strain distribution in your food. Okay, this is very much relevant because many of these patients who suffer from diabetes, they experience loss in sensation in the food. This is called as peripheral neuropathy. This can actually lead to balance impairment, and when the person is walking, he or she can be prone to falls. Okay. So this is a typical distribution that we are talking about. So we want to map out when a person is standing, how does the strain changes, strain, or what is the strain variation across the foot. Okay. So there is one. This was a work carried out in IASC probably 7-8 years back, where they had developed a FBG sensor based solution. They're not primarily, they're using 3 different sensing points, 3 for each foot. So you can see one at the top, one at the middle, and one at the bottom. And they were mapping out the strain distribution of these different different people. Okay, so that is quite possible using FBGs. We can map out the strain because we know that FBGs are able to sense strain. So when you naturally when a person stands on this platform, you can notice that there are FBG sensors. So there are FBG sensors here, here, and here, right? Three FBG sensors, and each of one picking the strain response of the forefoot, midfoot, and the hindfoot. Okay, so that's one application. Another application is, many of these contact sports like boxing, they use what the participants use, the players use what are known as mouth guards. So mouth guards are basically used to protect uh, any impact which can cause damage to the teeth. Okay, so many of these mouth guards which are available in the market, they do not go through a lot of quality check. Okay, so there was one study done where people wanted to check what is the impact or what is the quality of a mouth guard, whether it is able to really prevent the impact. Okay, so this was a study where they had created a model of the denture, and then they had um, used a mouth guard, and they have placed some FBGs at the mouth guard as well as at the denture. Okay, so you can notice that, and they created impacts using some balls, cricket ball, hockey ball, and steel ball. Okay, so you can notice here that the top three shows the impact that is created on the mouth guard, but the impact that is being sensed on the denture is quite low. Okay, so it clearly tells that the impact which is felt on the mouth guard is being not carried forward to the teeth, and the denture is pretty much safe. Okay, so that's another study done. Then there are also applications of FBGs in physiotherapy and rehabilitation. So this is one of these almost 10 years back, a paper where people have developed a sensing glove. So you can see that there are a lot of FBGs in each of the joints of the fingers. Okay, and you can notice that. So this is the person who is wearing the sensing glove, and he's emulating or he's creating a bend in the finger, and the computer program is able to emulate that, and in that way you are able to predict how much the person is able to move his finger. Okay, so many of these physiotherapy applications, the physiotherapist has no clue about how much the person is able to move his fingers or hands. It's mostly done through physical contact, based on the resistance offered by the patient is how the physiotherapist knows. But then this could be one solution where you can actually direct the patient to do certain things with the hand, and you can monitor it on the screen, and you have a direct way of predicting how things are happening, right? There's another interesting area which is coming up in gait monitoring application. So gait essentially represents the way that you walk. Okay, so every person walk in a different manner, right? So a gait is characterized by a gait cycle which has a stance phase and a swing phase. So stance phase essentially represents the time where your foot makes contact with the ground, and there is a swing phase where you actually, when your leg is not touching the ground. Okay, so it is it's getting popular because understanding the gait of a person can predict whether the person is prone to falls or not. Okay, so we have this knee. This particular example. There is a weight. It's used to monitor the angle of the knee the flexion angle of the knee. So you can notice that there is a stretchable band in which an FBG is placed, and then you keep it onto the attached to the knee of the person, and then as the person walks, depending on the strain that is generated on the FBG, you are able to map out what the angle. You can calibrate it to the angle, and that's how this is being used. Okay. So for this, basically for the knee movement tracking. Okay. So these are some of the biomechanical applications of FBGs. Now let's start talking about some of the biochemical sensing approaches. FBGs as such, they are not very sensitive to these kind of biosensing. Why? Because you need to, so the basic principle behind biosensing is you attach certain antibodies onto the fiber, and depending on the antigen which is present in the sample, which binds to the antibody, you need to create some changes in light. Okay, so the problem with FBGs is the fact that light is confined within the core of an optical fiber. And if you remember the image that I had shown in the beginning, the core is just less than 10 microns in diameter, and the cladding is something like 125 microns, right, in diameter, which means that the core is deep inside the cladding region. I mean, the core is embedded deep inside the cladding. So any kind of interaction that happens outside the cladding is not going to be influencing the light which is propagating within the core. Okay, so you need to deliberately make some changes in your gratings in order to be accessible to the in order to access the core, and those kind of so this is what I was talking about. When you do biosensing using FBGs, standard FBGs you cannot use for sensing refractive index changes because of the fact. So you could either etch off the cladding, remove some part of the cladding, or you can polish the fiber, or you can do what is known as tapering. Okay, or you do microfiber FBGs where you look at core only fibers and things like that. So there is some additional step that is needed to make the fiber sensitive, FBG sensitive to these kind of biosensing applications. You could also, so you can notice that the sensitivity will depend on the fiber diameter, I mean the overall fiber diameter in the core region. So here you can notice that, the cladding is pretty much thick here, having so much of diameter here, but in the region of FBG, we have deliberately removed a part of the cladding. Okay, you can remove it by chemical etching. You can remove it. You can also do what is known as tapering, where you pull the fiber and reduce the diameter of the fiber. Okay. In fact, recently people have started looking at biosensing using tilted FBGs. I think I talked about tilted FBGs, where the refractive index variations are at an angle. It's not exactly perpendicular. It's at an angle. So what happens is some of these light is getting coupled into the cladding modes. So this cladding is pretty much accessible to the outside environment, which means you can have interactions with the cladding, and looking at the cladding modes, you can predict whether the sample has the antigen or not. Okay, so you can notice here that the reflection spectrum is going to be something like this. In fact, this is a transmission spectrum. So you can notice that there is a core mode which shows a clear dip, and there are a couple of other dips which are representing the cladding modes. Okay, so the cladding modes would shift in response to the outside environment, and the core mode will not respond to that. Core mode will only respond to either temperature or strain changes. So some multi-parameter sensing using tilted FBGs people have started looking at. Okay, now this is another example where people have used, in fact, this work was also probably done in IASC, where they have used an etched fiber. So you can notice here that this is an etched fiber, cladding is removed, and this particular complex is coated on that fiber. Okay. So this is aminophenyl boronic acid reduced graphene oxide complex, which is coated onto that onto that etched region, and it is basically used for detecting glucose. So glucose will bind to this particular complex, and depending on the complex concentration or the amount of glucose, concentration of glucose, you will notice that the Bragg wavelength shift goes on increasing. So you can notice here that as the concentration of glucose increases, you can notice that the Bragg wavelength has shifted. And this is quite very specific to glucose, this particular complex, because if you repeat the same experiment with lactose, you can notice that there is no change in the Bragg wavelength. More or less, it's constant. But for glucose, there is a clear increase. Okay. Now there are also interesting applications, or I did not talk about this part, but there is also something which is picking up, which is called as a surface plasmon resonance based sensing approaches. So what is basically surface plasmon resonance? We are talking about the interaction of light with metallic regions. So light can actually interact with the electrons in the metal and create resonances. That's called surface plasmon resonance. And this typically happens in fibers which are coated with metals. Okay, so you can notice here that this is a fiber which has been coated with 50 nanometers of metal, and you can notice that there is some phenomenon here which shows a dip. That's called the surface plasmon resonance. Okay, so at that particular wavelength, the energy is being given to the electrons, and that is missing in the transmission spectrum. Okay, so certain compounds, so here for example glucose and glucose oxide, will result in etching of this metal, and because of etching, you can notice that the SPR phenomenon has disappeared. Okay, so you can find out what is the concentration of your particular compound which you are looking at. Okay, so this is actually a combination of, it's not just FBG alone, it's a combination of FBG plus SPR sort of application. Okay, now we move over to the last case study where we are planning to talk about biomedical sensing, basically monitoring physiological parameters. So this is one study where you are trying to monitor the blood pressure by the arterial pulse measurement. So arterial pulse is nothing but the pulse in your wrist. So for that, there is a watch-like structure which is being created, and you can see that there's an FBG sensor here, which is pasted onto a silicon diaphragm. Okay, and you can notice here that this is made in the form of a watch, and you can just tie this watch onto the person's hand, and you are making measurements of the so there's a comparison that's being made. The blood pressure has been measured using the electronic stethoscope and also using the FBG. So you can notice that there is a correspondence with the pressure that's being measured in the stethoscope as well as the FBG. Some of these robotic surgeries which are being carried out, so any kind of robotic surgery, it requires what is known as force feedback. And now what is this force feedback? When a surgeon is actually performing an operation, let's say he's using a knife and cutting a tissue, he knows how much force to apply. How does he know that? Because when you start putting your knife onto the tissue, you get a feedback. So you know how hard the material is or how soft the material is and how much force you need to apply. This is similar to, let's say you take an apple and you try to cut it. You're not going to do just like this, right? I mean, you know how much force to apply because you get a feedback. Now imagine a robot is performing a surgery, and when the robot is doing that, it has to, you cannot just program the robot and say that you need to apply this force. it is dependent on the patient, right? Each patient is different, each tissue is different. So how do you manage that? How do you start deciding how much force should the robot apply? Okay, so those things are made through the help of force feedback, and because the robot doesn't have intelligence as a human, uh, it needs to make decisions based on data that is gathered through sensors. Okay, so what happens is there are certain so this is one demonstration where an FBG sensor is being uh, is embedded onto the jaws of a microforceps module, and the force that is being experienced is being gathered through the strain that is captured by the FBG. Now that's quite interesting. This basically, especially in certain applications, certain surgeries which are done in the eye, the kind of force feedback that you get is, even for a human surgeon, it's below the tactile perception of the surgeon, which means the feedback that you get is not something which, as a human, also I cannot measure. Okay, so these FBGs come to use there as well. So this was a paper which was published in 2014. Now, as I told you, the world is moving towards a lot of smart textiles and wearable sensors. And surprisingly, not surprisingly, this FBG sensor is a potential candidate for embedding into textiles. You could start looking at applications where FBG sensors can be embedded into the textiles which are worn, and you could use wearable sensors like that. So these sensors are interesting because it helps in a continuous monitoring of physiological parameters, and very relevant because in India there is a very large group of elderly population who need assistance. So this can actually help improve the quality of their life. So this is a simple demonstration where an FBG sensor has been embedded or incorporated into the T-shirt using a Velcro arrangement. Yeah, there's associated electronic circuitry for that. And another important area where FBG sensors are finding application is in MRI compatible applications, especially in MRI imaging. And there are certain surgical procedures which need to be done under MRI guidance. So MRI, is nothing but a very electromagnetically polluted environment. A lot of interference that happens. A lot of you have the MRI frequency itself is quite. It can generate a lot of EMI. So that's when FBG sensors can be used for certain applications, which because of the fact that they are less immune to electromagnetic interference. Or I'm sorry, they're very much immune to electromagnetic interference, less prone to electromagnetic interference. Okay, so this is one of the work which I'm pursuing it in our lab now with our PhD scholar. So we are trying to look at embedding FBGs in PDMS. PDMS is polydimethyl siloxane, which is a silicon-based organic polymer. This is found to be very much biocompatible, non-toxic, and inflammable. So we are trying to develop FBG sensors which are embedded in PDMS, and we are trying to use it for certain applications. So of course, this image is picked up from this paper where they have developed a measuring probe. I think this was for the heart rate monitoring. They've used a drag rating embedded inside a PDMS. Okay, so they're essentially mapping out the ECG through the ECG, the heart rate that is being captured, and through this PDMS embedded FBG, they have a close match. Okay, so to conclude, there is a tremendous potential for fiber optic sensors in biomedical related applications, sensing applications. There are a couple of niche applications, and it offers a lot of multi-parameter capability as well. There are certain niche applications like MR compatible sensors. And if you want to have disposable sensors which are integrated to catheters and endoscopes, and also when you are looking at biochemical sensing with very little sample, a few microliters, you can go for optical sensing based solutions. However, there are a lot of challenges involved, especially adopting the technology to commercial use. Starting from the proof of concept level to coming to a product with a lot of this regulatory testing and all. You need to be aware of the need of end users, right? So finally, it's going to be used by a clinical lab or a doctor or a medical professional. So you need to really understand what is their requirement and accordingly, design products or design technologies relevant. So there are a couple of research opportunities in this area, primarily in terms of the sensor development, because this is not like you just buy a sensor from the market and then you can use it. It's not like that. There's a lot of process involved in terms of embedding the sensor, in terms of talking about thinking about patient safety, in terms of designing the instrumentation, so designing the entire sensor system. So there are a lot of opportunities there, improving the sensitivity and things like that. Then, as I told you, all these sensors require, FBG sensors, in fact, they require calibrations before you can do a real life application. So in terms of testing those calibrations, it's going to be challenging. There's also a need for low-cost interrogators. As I told you, one of the primary reasons why fiber optic sensing technology is not being adapted so much by the industry is because of this high cost involved. So, if people are if people can develop new low-cost technology, then we could actually just grab the market and make more products available out there. Okay, so these are some of the references I have used for my talk. Yeah, thank you very much once again for this opportunity. I'll wind up at this point. Thank you very much for inviting me over and giving an opportunity to share some of the relevant applications of biomedical using this fiber optic sensor, specifically fiber vibrating sensors. And I would also invite all of you to visit our institute, visit our lab. Of course, we're just starting off, but right now we have a small lab where we have all this characterization facility. So if any of you are interested, you are always welcome to our institute to visit, and we are open for those kind of visits as well. Yeah. So this is my email ID out here. In case you have any queries outside the session as well, you may please feel free to email me. We could take things offline as well. Yeah. Thank you very much. I would like now take questions from the audience.
Okay, participants can unmute and ask questions.
Yeah, you could either unmute or you could even type in the chat window.
Participants, if you have any queries, can ask now.
Okay. If there are no queries, I'd like to hear some feedback also, if that's possible, because I'm not really sure if you were exposed to this field of fiber optics. I really don't understand what the pulse of the audience is. Whether you were exposed to the area before. I mean, are you familiar with fiber optic sensors, or you're more towards the other spectrum, the biomedical spectrum? So you can share some views also.
Sir, one person asked one question, sir.
Okay, yeah, sure.
What is the recent technology in biomedical equipment?
Um, I really do not understand the question. Recent
What is the recent technology in biomedical equipment?
uh, recent technology in biomedical equipment. I mean, you need to be specific here, as in which kind of biomedical, uh, what kind of biomedical equipment you're talking about. As I told you, if you're asking about applications of FBG sensing in biomedical techniques. Most of the applications that I've talked about are in the in the proof of concept level in the laboratory and so on. But then there are certain technologies which are already commercialized. They are available in the market. For example, things like optical coherence for that matter. It's quite it's out there in almost all major hospitals that you talk about. But there are certain things like, for example, surface plasmon resonance based sensing and all. You don't have commercial products as of now. That's probably because these things are not in terms of you see a lot of publications in SPR related PCF sensing and all, but mm, but you're unable to take it up to the market because of the fact that the complete end-to-end demonstration in terms of the product uh, needs to be done, and then um, some making these fibers, for example, photonic crystal fibers. That's not that easy. There are practical difficulties available. Of course, you could do a lot of simulations and publish a lot of papers. But then, if you talk about the practical, experimental studies, I don't think there's not much efforts going on in India as far as that is concerned. Now, in terms of FBG sensing, yes, we have. So we do mostly experimental related studies. So we have created FBG experimental testing facility at our institute. But then, I'm a person who's not an expert in biomedicine, for example. My expert lies in photonics and fiber optics. We really need to understand what the demand of the biomedical requirements are, and then appropriately developing an instrument, so equipment, as you talked about. Yes. So that's the other challenge I was talking about. It's just not the sensor. Along with the sensor comes an instrumentation, equipment, instrumentation system, which builds an equipment. So making that cheap, it's probably challenging. And for example, a spectrometer, that, for example, whatever we have bought now in our lab, your source and the kind of spectrometer that we have, everything costs. The total cost is something over 10, between 5 to 10 lakhs. Now, that's not something which everybody can afford, and that creates issue. And for example, just imagine it. Um, just compare it with what you have in electronics. You have all these electronic sensors, for example, a thermistor or a temperature sensor or a strain gauge. They are like, but just cheap, very cheap and just available in the market and all shops and things like that. And if you say you want to build an electronic sensing system, you have a lot of microcontrollers, you have a lot of these development boards available, like the Arduino or the Raspberry Pi. Entire system you can build around it. Hardly going to cost you something like less than, let's say, 5,000 rupees. But compare that with the kind of infrastructure that you need for fiber optic measurement. So that's where things start to be taking a toll as far as fiber optic sensing is concerned. The kind of instrumentation that you need is pretty expensive. So that's what I said. One of the major drivers in fiber optic sensing is developing low cost interrogators that can really make a great change as we go forward. Okay, I hope I answered that question. I can see another question. For amplitude, no demodulation is needed, but for other, we need some demodulation. So in wavelength sensing, what type of demodulation is needed? Yeah, so that's an interesting question. The reason why you do not need a demodulation for amplitude is the fact that it is because the photo detector that you use in a sensing system is sensitive only to changes in amplitude. Okay, it is not sensitive to changes in phase. It's not sensitive to changes in wavelength. It's not sensitive to changes in polarization. So any other type of modulation that you're trying to use, you would always, if you want to use a photo detector, you should somehow convert that modulation to an corresponding intensity modulation. Okay? For example, if you're looking at phase demodulation, you have what are known as interferometers. So interferometer is something like, there's a very popular interferometer which is called as a Mach-Zehnder interferometer, where you have two fibers, you use two arms. One is called the sensing arm and one is called the reference arm, and then you combine those two arms together, combine those two fibers together. So what happens is that the phase change that happens in one of the arm is converted into corresponding intensity. So interferometers are basically used for phase modulation techniques, or phase demodulation techniques. Similarly, for wavelength demodulation, I talked about one technique that I talked about is this tunable laser or the edge filter technique, where you are converting that wavelength change to a corresponding intensity change so that you can read it out using a photo detector. Okay. Now, why do you do intensity change to intensity? Is because of this fact that photo detector can only sense changes in intensity. I hope I answered that question. Is that clear?
Thank you, sir. Thank you for answering. So there is another question, sir.
Yeah.
Which type of fiber is best suited for sensing application?
Okay. In terms of fiber, are you talking about the material? Then the standard fiber that is used for communication silica fiber. Okay, so that's basically glass. The problem with plastic or PMMA fibers is that they have a very large attenuation. So you cannot use it for example, you cannot use it for communication application where you're talking about hundreds of kilometers. But let us say you're talking about sensing application where you need only 10 centimeter long fiber. You could very well use polymer fibers. Okay? So there are a lot of that's not something which I touched upon today, but there are a lot of literature available on using polymer fibers, PMMA fibers, plastic fibers for sensing applications, especially in biosensing. Yes. So everything depends on what your application is, and but of course, when I should also mention that the FBG technology is primarily based on the glass fibers. It's not on plastic fiber. You can't create, or it's not like you can't create, but then it's quite difficult to make those kind of periodic changes in the refractive index of the core in PMMA fiber. It's not that easy. Whereas as far as glass fibers are concerned, the technology is quite developed, and in fact, the FBGs are available in the market as well. I mean, market, certain fiber optic components online stores where you can buy gratings. You can buy them. It's one grating is going to cost you something like less than $100. So like that, gratings are readily available. So you can start working on them as well. But the question was, what fiber is more suited? It depends on what application is, what is your cost, and things like that. Many factors come into play in deciding that. But the most common are fibers are those based on glass fibers. Yeah, I hope I answered the question.
Thank you for answering, sir. Thank you, sir.
Yeah. Any other queries?
Any other queries, participants? Okay. Thank you, sir, for this wonderful session. I convey my heartfelt thanks to Dr. K. Srijit, sir, Assistant Professor ECE in IITDM in Chennai, for providing us wonderful session on the diagnosis of in fiber optic sensors and also using fiber grating sensors. Thank you so much, sir, for spending your valuable time.
Thank you very much, madam. Thank you, the organizers and the institute for providing this opportunity to interact with this large crowd in this TBT sponsored conference. It was really a pleasure. Thank you very much.
Thank you. Thank you, sir. Participants, the feedback link has been posted in the chat box. And the afternoon session, you can join at 1:45 p.m. And Dr. Diana, sir, will join the session and give a talk on the biosensors. Thank you, participants. Thank you, sir. Participants can join at 1:45. Thank you.